All right, as our next example, I want to prove that we have a formula for the sum of squares. This is a formula that sometimes gets used when in calculus, in Calc 1 in particular, when you develop the Riemann integral. So this is somehow an integral that gets used to show that the integral of x squared is from 0 to 1 is 1/3. So this is somehow an integral that's tied up into that when you write out the Riemann sum for this integral. Anyways, what I want to do is just establish this, this formula for the sum of squares without having to worry about any applications of it. And so what we're going to do is, obviously we'll do this by induction. Our base case is going to be n equals 1. And we just have to check that the formula is valid for n equals 1. And let's think about this. If n is equal to 1, our left side it's going to be the sum of j squared as j goes from 1 to n. So that's 1 squared, or 1. The right side is going to be 1 times, let's see, 1 plus 1 is 2. 2n plus 1 is 3 over 6. We've got 1 times 2 times 3 over 6, which is 1. And in fact, these really are equal. The base case is true. Now for our inductive step. Okay, for our inductive step, what we're going to do is assume that this is true for some k. So we're going to assume that we have this formula. The sum of the squares from 1 to k is equal to k times k plus 1 times 2k plus 1 over 6. And we want to assume that that's true for some k greater than or equal to 1. And then we want to show, that the sum of j squared as j goes from 1 to k plus 1 is going to be whatever our formula is when n is equal to k plus 1. So that'll be k plus 1 times k plus 1 plus 1, so k plus 2, times 2 times the quantity k plus 1 plus 1. You can check that that's 2k plus 3 over 6. And again, this 2k plus 3 is 2 times, so just off to the side, 2 times k plus 1 plus 1. So that's 2k plus 2 plus 1, or 2k plus 3. You can check that. So that's what we want to show. Again, we want to somehow use our inductive hypothesis as we go along. We're going to start by looking at the thing that we want to prove something about, and that's the sum from 1 to k plus 1. And we've already kind of seen this story before. We're going to extract information about the sum from 1 to k by peeling off the k plus first term. So we're going to get what we get when this is when j is equal to k plus 1, plus what we get from 1 to k. Okay, so again, what we did is, without having to write everything out, I'm thinking of this as the sum of 1 squared plus 2 squared all the way up to k squared plus quantity k plus 1 squared. And so you can think of that as the sum of all the terms up to k plus, this is all the terms up to k from 1 squared, 2 squared, all the way up to k squared, plus k plus 1 squared. That's really what this original sum is. And so you can peel off that top term, and then you're left with the sum from 1 to k. The reason why we want to do that is that we have a formula for the sum from 1 to k, and that formula is the sum from j equals 1 to k of j squared is k times k plus 1 times a quantity 2k plus 1 all over 6. And then what we need to do is just a little bookkeeping, and what we're going to hope for is that this quantity, which is what we want it to be, and this quantity hopefully are equal. Okay, so that's what we want to know. Are these quantities really equal? And if they are, we're done. If they're not, something's wrong. So let's check that. And rather than dealing with cubes, one thing that we can do to make life a little easier, and actually let's just right away multiply and divide by 6 so we can just deal with the fractions. We have the 6 in the denominator like we want. That part's fine. One other thing that we can do that's nice is you can factor out a k plus 1 out of both terms. You can factor out a k plus 1 from there and the k plus 1 there. And so let's do that. So we're going to factor out a k plus 1. We already have our 6 in the denominator, so this is looking good. And then let's see. What we're going to be left with Well, over here, if we factored out a k plus 1, we're going to be left with a 6 times a quantity k plus 1. On this right fraction, after we factor out the k plus 1, we're going to be left with k times quantity 2k plus 1. And then if we simplify this, this is going to be k plus 1 times, let's think about what we're going to get here. This is going to be k times 2k will be 2k squared. This is going to be 6k plus 6 plus k. So that's going to be 2k squared plus 7k plus 6 all over 6. And then how does that factor? This happens to factor as, you can factor out a k plus 2 and you're left with 2k plus 3. It might actually be easier to see this going backwards. If you can factor that, everything's good. You can also just go backwards. You get k squared, 2k squared plus 4k plus 3k, so there's your 7k, plus 6. So these really are equal, and that completes the proof.